Question 12. A portable scientific sensor uses a rechargeable battery that is initially fully depleted. It is connected to a 12-watt charging unit for 1.5 hours. The charging system is only 75% efficient. During charging, the battery management system diverts 0.8 watts to operate internal electronics, so only the remaining useful power contributes to stored energy. Calculate the total energy stored in the battery after this charging period. This problem tests our understanding of energy efficiency of devices. Let's begin by recalling what we know. We know that rechargeable batteries store chemical energy, which comes from the electrical energy supplied during charging. This energy can later be released to power devices. We also know that efficiency describes the ratio of useful energy stored to the total energy supplied. Not all input power contributes to stored energy. Some is lost as heat or used by internal circuits. Finally, we know that electrical energy supplied is the product of power and time, meaning that the total energy delivered depends both on how much power is supplied and for how long. Now let's work through the solution step by step. We begin by considering the efficiency of the charging system. Efficiency is defined as the ratio of useful output power after losses to the total charging power supplied. In this problem, the efficiency is given as 75%, which we write in decimal form as 0.75. This means that only 75% of the charging power remains after efficiency losses. Next, we calculate the power that remains after this efficiency loss. We do this by multiplying the efficiency by the charging power. So the power after efficiency equals 0.75 multiplied by 12 watts. Carrying out the calculation gives a value of 9 watts. This means that after the inefficiencies in the charging system, only 9 watts of power remain available. However, the problem also tells us that part of this power is used by the battery management system to operate internal electronics. The internal electronics consume 0.8 watts, so we must subtract this from the power that remained after efficiency. The useful charging power is therefore the power after efficiency minus the internal power consumption. Substituting the values, we calculate 9 minus 0.8. This gives a useful power of 8.2 watts. So only 8.2 watts actually contributes to storing energy in the battery. Next, we calculate the total energy stored. Energy is given by the relation energy equals power multiplied by time. The useful power is 8.2 watts, but we must be careful with the time units. The charging time is given as 1.5 hours, but energy calculations require time in seconds. So we convert hours into seconds. 1 hour equals 60 minutes, and 1 minute equals 60 seconds. This means 1 hour equals 3,600 seconds. Therefore, 1.5 hours equals 1.5 multiplied by 3,600 seconds. This gives a time of 5,400 seconds. Now we substitute the useful power and the time into the energy equation. Energy stored equals 8.2 multiplied by 5,400. Carrying out the multiplication gives 44,280 joules. Finally, we express this in standard scientific notation. This is approximately 4.4 times 10 to the power of 4 joules. So the total energy stored in the battery after the charging period is approximately 4.4 times 10 to the power of 4 joules. This is our final answer. What did we do? First, we used the efficiency of the charging system to determine how much of the 12-watt input power remained after losses. This gave us 9 watts. Then we accounted for the 0.8 watts used by the internal electronics and subtracted it to find the useful charging power of 8.2 watts. After that, we calculated the energy stored using the relation energy equals power multiplied by time. Finally, we converted the charging time from hours to seconds and multiplied by the useful power to obtain the total stored energy. Now let's consider common mistakes or misconceptions. If we ignore the 0.8 watts used by the internal electronics, we would assume that all 9 watts goes into storing energy in the battery. This would lead to an overestimate of the stored energy. Another common mistake is forgetting to convert the time from hours into seconds. If hours are used directly in the calculation, the result will be incorrect by a factor of 3,600. To summarize the key ideas from this problem, only a fraction of the input electrical power supplied to a charging system actually becomes stored energy, because some energy is lost due to inefficiencies such as heat. In addition, battery management systems often consume a portion of the available power, which further reduces the net power used for charging. Finally, the stored energy in a battery is calculated by multiplying the useful power by the charging time, making sure that all units are consistent, especially converting hours into seconds when necessary.